Hello, welcome to lecture number 22. In the previous lecture, we derived the shallow water equations, and we said that the shallow water equations, the model or the equations, the set of equations is a good model to understand barotropic waves, that is, waves where or processes which do not depend on the vertical structure of the ocean. Now we'll see how linear waves emerge, how linear waves can exist, can be supported in these set of equations, and to do that we have to linearize the governing equations that we had derived previously. So let's start with linear waves. Now to have a linear version of these equations, you can imagine the terms that we'll have to throw out, or let's go back to the earlier form that we had derived. You can see that which are the nonlinear terms. You can take a moment and then you can find out yourself the nonlinear terms. So this is a nonlinear term, this is a nonlinear term, this is a nonlinear term, this is a nonlinear term. So these are the terms that we'll have to throw away from the momentum equations to have linearized version of the system and to understand linear waves. So we now have the linear governing equations. So del u del t. Remember that we derived the shallow water equations with the assumption that there is no vertical variation. Now we are putting an extra assumption that the system should be linear. That is, the amplitudes and the derivatives are not big, and we can neglect the nonlinear terms. So these are the momentum equations in the x and the y directions. So we have all linear terms, and the advective terms were neglected. The terms that are marked in red here are neglected with the assumption that the Rossby number which is equal to u by omega L is much less than 1. That is the case, then we have the Coriolis acceleration, which is dominating over the convective acceleration or the advective acceleration terms. So when is this achieved? This Rossby number much less than 1. This is achieved within flows where we have, or rather we can go to the next page. So this is achieved for flows where we have weak velocity field, or we have fast rotation, or we have large scales. This gives rise to the combination u by omega L to be much less than 1. So we now introduce a new scale. So if you recall, we had done in the non-dimensionalization chapter or topic, we had introduced scales for velocity, we had introduced scales for length. Now we introduce a scale for the wave speed. We started with, we have a system, a shallow water system, and we want to understand waves. So let's define a scale for wave speed. So let's define, or let's actually denote C as the scale for the wave speed. So C is, here we are taking it as the capital C. Wind is also just a variable for us to keep track of. So we denote it as the scale for the wave speed. Now This is a ratio this is defined as the ratio of the distance L, which is the characteristic distance in the problem, and the time scale capital T. Remember that this is different from the flow speed. This is a scale for the wave speed, and C is equal to L by T, and in this case this is much larger than the flow speed itself. Okay, so the information propagation is happening at a much larger scale than the propagation of a certain material from one point to the other. So this is where, I mean, for example, if you have a disturbance at a certain location, the disturbance information propagates much faster because the wave energy is propagating. The wave is taking the information that there was a disturbance at a certain point, whereas a material at that point does not go as fast as the wave. Okay, so it can travel, but in most cases the velocity of the particle at a certain location can be much smaller than the propagation of the information about the disturbance at a certain point. For example, in a stadium, let's say there are people who are making a certain wavy pattern of disturbance, and the disturbance propagates to the whole stadium very soon, whereas a certain person is actually not moving and taking along that information. So that's the difference between the wave speed and the particle speed, or the flow speed here. So velocity is small, much smaller than the propagation speed of the disturbance. So the continuity equation we have already written down. We'll write it down for the sake of completion. So for flat bottom, so expand the continuity equation. To get del eta del t plus u del x plus v del eta del y. Okay, so now let delta h be the scale for vertical displacement. Delta h be the scale for vertical displacement eta. Then the order of the terms in the previous equation, go back to this continuity, the form of the continuity equation. Please verify that the order of the terms in the above continuity equation is delta h by t, given that the first term is del eta by del t, The second term is u del eta del x plus v del eta del y. So the order of the terms is u del h by L. Then the third term being h del u del x plus del v del y. The order of the terms is h u by L, and the order of the fourth term, which is eta del u del x plus del v del y, is delta h u by L, given the fact that we have chosen delta h to be the scale for the vertical displacement eta. Now, taking the ratio of 1 by 1 and 2, ratio of 1 and 2 and 1 and 4, we have that delta h by t and u delta h by L. This gives us L by t times 1 by u. Now, given the fact that L by t is much greater than u, we can given the fact it is much greater than u, we can neglect 2 with respect to 1. Similarly, for this ratio 1 by 4, we have delta h by t, and same delta h u by L, which gives rise to L by t and 1 by u. So the numerator is much greater than the denominator, hence the term, the first term, that is 1, dominates over 2 and 4. Hence 2 and 4 can be neglected with respect to the term 1. Hence the form of the continuity equation now reduces to del eta del t plus h del u del x plus del v del y equal to 0. Now, for this balance to hold, delta h by t should be of the order uh by L. Hence, delta h by t is equal to is of the same order of by L, which gives delta h by h ut by L. Now, given the fact that L by t is equal to c, capital C, that is the scale for the wave speed that we had defined actually earlier when we had introduced that scale, we know that if that is the case, then delta h by h is now equal to u by c, because L by t is by definition is the wave characteristics, is the scale for wave. And again, we said that this u by c ratio is much less than 1, because wave information is propagating much faster than the particle propagation, and this is much less than 1. Hence, we have the condition that the displacement should be much less than the total height of the water column. Okay, so this is what we get after linearization. So this is a restriction that is being placed on us, that our displacement for the system, for the linear system to be valid for, should ensure that the displacement, surface displacement, is much smaller than the total height of the water column. So we'll see now the formation of a certain particular type of wave called Kelvin wave in these systems. So let's see what are the characteristics of this waves, these special types of waves. Okay. So the reason why I mentioned barotropics specially is because baroclinic Kelvin wave can also exist. They can exist in the interior of the ocean also, and hence to distinguish it from that, I say that this is a barotropic Kelvin wave, because now we are dealing only with barotropic condition. We are dealing with homogeneous condition, that is the variation, there is no variation of properties with depth. We will not go into the details of internal Kelvin wave, but we will show what the properties of internal waves in general. But for this discussion, we are sticking to barotropic waves. So this is a form of wave that require a lateral boundary to travel. In oceans, it travels along the coastline. So the ocean ocean is bounded by coastline in most places, and these Kelvin waves can be seen moving along coastlines from one country to the other, and we will see what are the properties of this barotropic Kelvin wave. So baroclinic Kelvin wave can also exist, as I mentioned, but we are only interested in the barotropic version here at this point. So this is the schematic of the system that we are going to talk about. So this is x coordinate, this is y coordinate, and this is eta, and this is the valve. Okay, assuming that this is the continent, and this is actually prohibiting the wave to pass beyond this direction. Okay, there is it's stopping it here at this valve. So this is a simple schematic of the situation that we are talking about. So consider a single layer of fluid which is bounded below by a horizontal bottom. So the upper surface is free, the coast is along y-axis, so this is the coast, x equal to 0. Now at the coast, which is at x equal to 0, at this location we have a peculiar condition for velocity u, because there is an impermeable boundary condition, that is the water or this fluid cannot go into the into the land. We need to have a condition that the velocity u is equal to 0, that is the x velocity at the coast is equal to 0. Now, Lord Kelvin, who actually was name is Sir William Thomson. So he was a Scottish scientist and an engineer. His insight was that why don't we try looking for solutions which have u equal to 0 everywhere. Okay, remember I said u equal to 0 at the coast is a necessity for the boundary condition, but the insight of William Thomson, who became Lord Kelvin later on, said that let's look for solutions where u is equal to 0 everywhere. Remember the difference, it's not only at the coast, but look at solutions for u equal to 0 everywhere. Now let's try why did he say that, and let's see what happens if we do that. Now putting u equal to 0, in the linearized shallow water model, we have so writing down the full equation, so put u equal to 0 in the set of equations from 2, we have del v del t is equal to minus g del eta del y. Now differentiating with respect to time, del square v del t squared is equal to minus g del square eta del y del t. So let's call this equation 4. From equation 3, we have del eta del t h del v del y equal to 0. Differentiating with respect to y now, del square eta del y del t. You can imagine why I am doing this. Del square v del y squared equal to 0. So from 4 and this part, let's call this 5. What we get is del square v del t squared plus gh del squared v del y squared, sorry, is equal to gh del square v del y squared, and this can be represented as del squared v del t squared is equal to c squared del squared v del y squared, where c is equal to root gh. So this is actually small c. So remember, this is the small c. This is, we're just saying that let us call this variable, I mean let's call this a c, and is equal to square root of gh, and this is different from the scale c for the wave speed that we had introduced. This form, if you recall from your advanced mathematics, this is the form of, this is a wave equation. It's double derivative in time, double derivative in space, and both of these are related by a certain constant. So this wave equation represents the propagation of a one-dimensional wave. The general solution to the above equation is V. We are looking for solution V is equal to V1 x comma y plus ct plus V2 x y minus ct, where V1 and V2 are some constants and these are waves traveling in opposite directions. Now, using the y momentum equation, dv dt minus g del eta del y. Okay, we'll use this momentum equation, but first let's expand this dv dt in terms of a variable and apply the chain rule in terms of a variable xi. Okay, here xi is defined as the variable y plus ct. Now, as d psi by dt is equal to c, so del v by del t is equal to c del v by del xi. This is equal to c del v by del y plus ct, and this is equivalent to having c del v del y. Hence, from this equation, this is the y momentum equation, hence c del v del y is equal to minus g del eta del y. Okay, just using the y momentum equation and the fact that we can expand the time derivative using the chain rule, and this is the derivative with respect to y plus ct is equivalent to derivative with respect to y. Ct is just a translation. So this gives us so this equivalence between, this equality gives us the form of the surface elevation, this eta, as minus h by g v1 x comma y plus ct plus root h by g v2 x comma y minus ct. So this is the form of the surface elevation in terms when we assume the u velocity to be 0, that is, in a Kelvin wave formation situation, this is the surface elevation of the free surface. And this is where we stop this lecture, and in the next lectures we will derive, we'll just see, we'll simplify these forms and we'll see the implications of setting u equal to 0 and how how a Rossby radius of deformation comes in, and how that is important in setting, how actually it's important in dictating the dynamics of the Kelvin waves. Thank you.